All right, so as of now, we are online and we will continue talking about some distributions. I'll go specifically here today on the example of the bivariate normal distribution, and we will use it to answer one question. So we talked last time about the multivariate normal. Multivariate normal distribution. Notation was M and mu sigma, where sigma is the variance covariance matrix and mu is the vector of means. And there was this theorem that if y is equal to a times x, then y follows a distribution that has this normal with m. The mean is going to be a. I actually added, there was a b here, ax plus b plus a times the mu of x plus the vector b. And the variance covariance matrix was a sigma a transpose. So when we have a linear transformation of a normal vector to which we're adding a constant vector b, that b does not affect the variance covariance matrix. You see, b is only in the mean. It has nothing to do with variance. So adding a constant to a vector does not change the variance. What it changes is the mean. That constant is added to the mean of the vector. So that's what we did last time. And so today I'm going to use that once more, but go specifically in the case n equals 2. When n is equal to 2, we talk about the bivariate normal. Here we have x is x1, x2. Mu is mu1, mu2, which is mean of x1, mean of x2, and sigma, in this case, is sigma squared 1, sigma squared 2, which is variance of x1, variance of x2, and off diagonal here, we are going to have the covariance of x1, x2. And usually, I would say here it's rho sigma 1, sigma 2, rho sigma 1, sigma 2. Remember that the rho, by definition, is equal to the covariance divided by sigma 1, sigma 2, right? That's why I can just replace here covariance by rho sigma 1, sigma 2. This is by definition covariance of x1, x2. Now we consider y equals x1 minus x2, x1 plus x2 minus 1 and plus 2. So we have this vector y. And the question is, find distribution of y. B, under what condition are x1 minus x2 and x1 plus x2 independent. This is the problem. It's a modification of a problem that is in your book. Something we need to know how to do. So I'm going to take this problem. Notice that I didn't tell you in this problem what is sigma square 1, what sigma square 2, what is rho. You know none of that. And what you need to do is figure out what is going to be the distribution of this vector and under what condition the two random variables x1 minus x2 and x1 plus x2 are independent. So to answer the question, obviously you've got to use this because that y is a linear combination of the vectors x, the components of the vector x, which are x1 and x2. So you start by that. Determine A and B, and then write down what is A transpose sigma A, or A sigma A transpose, and then find out what is A mu plus B. So start by so we'll say y is nothing but this 1 minus 1, 1, 1 times x1, x2 plus minus 1, 2. That's what the vector y is, which is 1 minus 1, 1, 1 times x plus minus 1, 2. And thus, that's the vector B, and this is A. So once you have A and B, what you need to do is to get the mean of y. So mu y is A mu plus B. A is 1 minus 1, 1, 1 times mu1, mu2 plus B, which is minus 1, 2. So that is mu1 minus mu2 minus 1, mu1 plus mu2 plus 2. So that's the mean of the vector y. And now to find the variance covariance matrix, it's A sigma A transpose. A is 1, 1 minus 1, 1. And sigma is sigma square, sigma 1 square. I don't know why I always turn to put this 2 below. Sigma 1 square, sigma 1, sigma 2 rho, sigma 1, sigma 2 rho, and sigma 2 squared. And now you transpose this. It's going to be 1 negative 1, 1, 1. And all you have to do now is the algebra. So let's go ahead and do the computation. So that is sigma 1 squared minus sigma 1 sigma 2 rho, then sigma 1 sigma 2 rho minus sigma 2 squared, sigma 1 sigma 2 rho plus sigma 1 squared, and then sigma 1 sigma 2 rho plus sigma 2 squared that you multiply by this guy. And you take that times this. So what's going to happen there? Because sigma 1 squared, sigma 2 squared, and then minus 2 sigma 1 sigma 2 rho, right? Agree? This times 1 plus this times negative 1. Then you multiply here and you add. When you add here, what happens is that this guy cancels with that one. So you have sigma 1 squared minus sigma 2 squared of diagonal here. Then you multiply this and subtract that one. These guys cancel again, and you have sigma squared 1 minus sigma squared 2. Then you multiply by that one and you add. What you're getting is sigma 1 squared plus sigma 2 squared, and then plus 2 rho sigma 1 sigma 2. So y follows bivariate normal distribution with mean. That mu y you just wrote and sigma y that you just wrote here. Now to answer the second part of the question, which is part B, you need to know that a multivariate random, the components of a multivariate normal vector are independent if their matrix, if their variance covariance matrix is diagonal, as we had in the example in the last lecture. So the off-diagonal elements are 0. If the off-diagonal elements are 0, then they are independent. So, and you can see they are same. So the off-diagonal elements are same if equal to 0, if sigma squared 1 equals sigma squared 2. So if the two random variables that you start with have the same variances, then no matter what is the correlation, x1 minus x2 and x1 plus x2 are going to be independent. Now, quick question. My y is not exactly x1 minus x2 and x1 plus x2. Why can I conclude based on this that x1 minus x2 and x1 plus x2 are going to be independent anyways? Because the question is about x1 minus x2 and x1 plus x2. But y is minus 1 and plus 2 here. And I want to base my reasoning on this and just conclude that x1 minus x2 and x1 plus x2 are independent. Why will I be correct if I do so? From the work that is done, we can conclude that x1 minus x2 minus 1 x1 plus x2 plus 2 are independent. That's not what our question was. Our question was x1 minus x2 and x1 plus x2 are independent. Now my question is, why can I conclude from this that x1 minus x2 and x1 plus x2 are also independent?
Just take the constants off.
What?
Can you just take the constants off?
The question is, why will it be okay to do so? You always remember one thing, the definition. What does it mean that they are independent? Hmm? Okay, that's another way to see it. If we are talking specifically about normal distribution, then yes, that's correct. That's one way to see it. It's a multivariate normal distribution, so the mean plays no role in the independence and the constants goes only into the mean. So if the two are independent, then x1 minus x2 and x1 plus x2 are independent because they are jointly normal. That's a correct answer. But if they were not normal, it's very important every single word that I give in that statement. Yeah. Because if they are not normal, it's not correct. When do we say that two random variables are independent? It's in the notes, you can open and read. Anyone looking for that?
Said when the Israel David said to be independent.
When do we say that two random variables are independent?
When the occurrence of one did not affect the other.
Okay, what does that mean in terms of their distributions? Joint distribution is the product of distribution. That's the basic definition of independence of random variables when you have distribution. Same when you have PMFs. Two random variables that are discrete are independent if the probability of any two elementary outcomes join is equal to the product of the marginal probability. And some of that you have on the homework that is supposedly due tomorrow or after tomorrow. If you're not answering me, it means you haven't completed that yet, which is also a serious problem. Because it's moving fast. Very soon it might get late to answer the questions. So, if the joint distribution of this vector and the other one is the product, how from this can we conclude that the joint distribution of these two is going to be equal to the product? Technically, this is not more answering the question, the original question, because you already answered that question. We're in the case of the normal, so we can conclude that they are independent because the variance covariance matrix is diagonal. B doesn't affect that, so we can drop B as well and still have independence. Now we want to show this. How can we show this from that?
If we use transformations in terms of default.
Actually avoid talking about that because it's not part of this class as far as I'm concerned. Because if I want to explain that, I will have to do things that people have not studied in other classes. That's why I don't use Jacobians and I didn't do transformations as well. You're using that on your homework and you're doing too much more than necessary. But it's not a bad thing if you know that.
No, I didn't know.
So technically, if I say, what's the probability that x1 is less than little x and x2 is less than little y? If I say that this thing is equal to the probability that x1 is less than x times probability that x2 is less than y, is it not true that probability that x1 plus c is less than x plus c, x2 plus d is less than y plus d is equal to the probability that x1 is less than x plus d plus c, sorry, times probability that x2 is less than y plus d. This is not true. Huh? It's obvious because all I did is add c to each, add c here, add c here. I can cancel them. I can cancel the d's. Cancel here, sorry, d here. What's d? I can cancel the c and cancel the d's. And that is this thing is exactly same as that and when you rewrite it this way, it means completely something completely different. That these random variables are independent. So adding or subtracting a term to a random variable does not affect independence. Most of the time, the question that I ask straight in the class don't need you to go look for answers somewhere else. Just look at the definition. That's what it is. All right. And so here, x1 and x2 play the role of these two vectors. And y1 and y2, the original guys. All right, let's go to the other distributions that I wanted to talk about. We'll have to go back to the Bernoulli distribution. So we have talked several times about the Bernoulli distribution in this class. How do we define that random variable, the Bernoulli one? What do we call Bernoulli random variable?
With random variable, one term probability at one is P. And it's zero from
It's a random variable that has two values, 1 and 0, with probability of 1 equal P and probability of 0 equal Q. 1 is regularly assigned to what we call success and 0 to what we call failure. They don't come in real life in 0 1s. You are the person who defines what is 1 and what is 0. So you run the experiment and you choose what is 1 and what is 0, because 1 means success and 0 means failure.
Dr. Longla,
Yes.
Melissa got kicked out. She's in the waiting room.
Thank you. So two values, 0 and 1, where it's P equal probability of X equal 1. 1 is called success, 0 is called failure. And we had the expected value of this random variable equals to P, and the variance equals to P times 1 minus P. That's what was done. Now today I wanted to use that distribution to define something else. The negative binomial distribution. The parameters R and P. So from the Bernoulli distribution, we defined last time what we call the binomial distribution. The binomial distribution, which arises from repeating independent Bernoulli distribution, repeating several times the same experiment, which has outcomes following the Bernoulli distribution, and then counting the number of successes, and the variable that is equal to the number of successes is called the binomial variable. That's what we have. Now, if in this case, what we call the negative binomial distribution here is, we have encountered already this distribution in one problem. It's when you are repeating that Bernoulli experiment, but you're not just counting the successes, you're counting the failures. And you have a certain number of failures that you are allowed to have. Once you reach that number, it stops. You can't continue, right? And so you repeat, and you're focused on the number of failures. You want to model and figure what will happen before you reach R failures, for example. Right? So here, define Y as being the number of successes before This is what is of interest. Before the R failure. So you, as you're rolling, you're failing and you don't care until you fail R times. When you fail R times, you stop. So how do we find the distribution of such a random variable? So how do we understand the form? You start rolling 1, 2, 3, 4, 5, continue until you reach R minus 1 failure. Somewhere there, and you continue rolling. If you are to stop at N, then here where you stop, that's N. At N minus 1, you shouldn't have R successes. R failures, and your failure should come right after that. This is how you begin to understand that formula. So you start here, first row, 1, 2, 3. Somehow there you are accumulating your failures. And just prior to the last failure, which is the R failure, you don't know what is happening, but you just know that for sure, before that, you have R minus 1 failures. Okay. And you want to stop here. And you want the whole thing to be made of N. You want the, let's say, not to take N as we were used to before, call this Y, that's the variable. So you want Y trials, among which before Y minus 1, right here where you stop, that's Y minus 1. Before Y minus 1, you have R minus 1 failures, and your R failure is the last one. Right there. So what you have here is Y minus 1 position, Y minus 1 position. Sorry. Sorry, I'm doing something here. Keep my N where it was first, and then I'm going to put the link between the N and the Y, so it's not going to be it's N minus 1, not Y minus 1. So N minus 1. Changing this. This is Y is the number of successes, not yet the number of everything you have. So before here it's N minus 1 guys. So the N total that I have, which is the number of experiments that I have, is Y plus R. Number of failures plus number of successes is the number of trials, right? You take all your failures, you add to all your successes, you get all the experiments that you ran. Do you agree with that? You can't have an experiment that is both a failure and a success. But now, from this number here, you are subtracting 1. That's what is here now, -1, n minus 1. So n minus 1 gives you what is before that last trial, that is giving you the last failure. So this is what you're subtracting 1 from. How many failures are before that last one? R minus 1. Where are those failures? That's the question. Do you know their positions? You don't know. You don't know the positions of those failures. That is why you are trying to figure where you're going to put those R minus 1 failures in the Y plus R minus 1 position, which are there. N minus 1, which is Y plus R minus 1. So you have Y plus R minus 1 positions where you need to put the R minus 1 failures. And then, because they all have the same probability, the probability of a failure doesn't change from one experiment to another. So they have the same probability, which is 1 minus P, right? So that is 1 minus P to what power? Multiplied because they are independent. So the probability gets multiplied. What should be the power? How many failures are there? Huh? R minus 1. And how many successes are there? And then there is one thing that is left, the last experiment. What is there? Failure, which is another 1 minus P.
You said P to the Y is our successes,
Yes,
and 1 minus P is the failures.
the last failure. You have R minus 1 failures and Y failures before the last failure. So R minus 1 failure, Y successes, and you still have one failure left, which is the one that is coming to close your experiment, because when you get that R1, you stop. That's this 1 minus P. And this is choosing where to put those failures among the Y plus R minus 1 positions that you have. And so that is what gives you the formula that you have to find the probabilities in this case. And so what are the possible values of Y here? Okay. it's 0. Maybe there is no success. 1, 2, and so on. All the way to infinity. Successes can go up. You can play all your life and not have to add failures.
But I thought you said the experiment stops when it reaches R prime.
Yeah, but if you don't have it,
Oh,
you keep playing. That art failure, that last one, can come when you die. If you're very lucky, right? The chance is small, but it is there. Because as Y is growing, it gets smaller. All right. Now, so with the Poisson distribution, we have also it's a discrete random variable. Probability that x is equal to x is e to negative lambda times lambda to the power x over x factorial, for x equals 0, 1, 2, so on, all the way to infinity, and 0 elsewhere. Here, lambda is the mean and variance. This distribution is important in modeling the arrival times. And it's good for processes that have a mean per unit. Sometimes the unit can be time, the unit can be volume, the unit of volume, the unit of surface, depending on whatever you're studying. If you are sure that the mean occurrence per unit is fixed, equal to a lambda, a given lambda, it's good to use the Poisson distribution to model that. The moment generating function here is mx of t for e to the lambda times e to the t minus 1.
These are lambda is mean and variance.
Yes, both. That's some of the examples of discrete distributions that I wanted to talk about now. Here, it's really not important. The only thing I can ask you to do with this as of now is just to plug in x and lambda and find the probabilities for now. Later on, we'll do more things with that. Other distribution tool will be the gamma distribution. Parameters alpha and beta. It's a continuous distribution that has two parameters. The density is 1 over gamma of alpha, beta to the power alpha, x to the power alpha minus 1, e to the negative x over beta. Beta is called the scale parameter. Beta is called the scale parameter. It answers for the spread of the graph, right? Your x is positive, 0 otherwise. The moment generating function. If you compute, you get 1 minus beta t to the power negative alpha for t less than 1 over beta. Alpha and beta are positive numbers, okay? The mean is mu equals alpha beta, and the variance sigma squared is alpha beta squared. When alpha is equal to 1 for this distribution, you obtain the exponential distribution that we discussed earlier. So when alpha equal 1, you get the gamma 1 beta is exponential beta. When beta is equal to 2, and we denote alpha as r over 2, we obtain chi-square distribution with r degrees of freedom. So that's chi-square chi-squared distribution with r degrees of freedom. And what is good about this distribution is that when you have a fixed beta,
Alpha is what over 2.
what?
Oh, when beta beta is equal to 2 alpha is
R over 2. If we denote alpha R over 2, then R is the degree of freedom. Like say if you're writing gamma of 2, 4, then it's high squared 2 times alpha. Alpha is 4, 2 times 4 is 8. Exercise. ID random variables with f of x equals e to negative x. Otherwise, a find distribution of y equals minimum of x1, x2, x3. With distribution f of x equal e to negative x. Independent and identically distributed. How do we find this distribution? I say, okay, what's the probability that y is less than little y? We want to find it out. Y is the minimum. And when you think of the minimum, you see 3 variables and you want to put the number y, you want to put this number y somewhere between the variables x1, x2, and x3. You don't even know which of them is smaller than the other. So it's better to go to the complement, because perhaps if y is, it's hard for you to figure that out, then perhaps you can put that little y below the minimum. If it's below the minimum, then for sure it's below every single one of them. That's why it's good here to go to the complement. And that is 1 minus the minimum x1, x2, x3 is larger than y. If the minimum is larger than y, then for sure each of them is larger than y, right? And if each of them is larger than y, then for sure the minimum is larger than y. So the two events are same here, that x1 is larger than y, x2 is larger than y, and x3 is larger than y. These events are same. But you can't say the same about this one here. Pulling the y in between the x1, x2, and x3, you can't do that. Now, because these are independent random variables, this probability is equal to the product. And because they are identically distributed, this product is just one of them raised to the power 3. And you can compute the probability that x is larger than y. From that, it's the integral from y to infinity of e to negative x dx, provided that y is positive. That is negative e to negative x, which is nothing but e to negative y. Therefore, probability that y is less than or equal to 1 is 1 minus e to negative 3y. When y is larger than 0, 0. Otherwise, we've lost the Melissa again. And what distribution is this? That? No, well, when you say gamma, you gotta give me the parameters. What are the parameters if it's gamma?
Alpha would have to be 1.
Beta is 1/3, yeah. And what happens when you have gamma with alpha equal 1? How do we call it? It's exponential. That's the exponential distribution.
It doesn't explain one.
What?
It doesn't explain one at the beginning. 1 minus.
This is the CDF. Take the derivative of that. You have the PDF. Little fy of y is equal to 1/3 e to negative 3y. Sorry, 3 e to negative 3y, not 1/3. Take the derivative of this. That's what you get. What we got here is CDF. So yes, in fact, that's the exponential distribution. Now, depending on how you put the parameters, you could call that exponential with parameter 3 or with parameter 1/3, depending on how you're putting your parameter in the distribution. And the two ways work. So there are books where the exponential is with e to negative x over beta, and in other books it will be just e to negative beta x. And depending on what you start with, you know that when you're writing that down, you mean something, right? So if you have to be consistent with what the beginning of this lecture said, that will be 3 to the power minus 1, because our beta from the definition is x over beta. So in that case, this would be exponential with parameter negative 3 to the minus 1, which is 1/3. Any questions? If not, then there is one last guy here called the beta distribution. And next time we'll start talking about statistical analysis, how to use all these names and things to answer statistical questions. Also has 2 parameters. And they have x. X is x to the power alpha minus 1, 1 minus x to the power beta minus 1 over beta of alpha beta, where beta of alpha beta is the function, the beta function. Here you want 0 to be x to be between 0 and 1 and 0 otherwise. So the density of that function is between 0 and 1. Everywhere else it's equal to 0.
What do you have on the bottom?
Beta. So beta is nothing but the integral from 0 to 1 of what is inside there. And it's a special function. One of the old questions that we had was find C such that f of x equals cx times 1 minus x cubed. 0 less than x less than 1. 0 otherwise is a CDF, is a PDF. How would we answer the question in this case? This is C, and you would say this is x to the power 2 minus 1. 1 minus x to the power 4 minus 1. And so you would say C is equal to 1 over beta 2, 4. Now go ahead and take those integrals. Why beta 2, 4? Because this is the formula of the beta distribution, and the only thing that is missing is the constant 1 over beta of 2, 4. All right. Is there any questions? Anything we did today, any question? Every last thing I can add for you here would be if u of the beta is equal to alpha over alpha plus beta, and sigma squared is alpha beta over alpha plus beta plus 1 times alpha plus beta squared. These two might be handy at some point. As of now, it's not useful. Right. If there's no more questions, then we shall stop here today.